Okay, let's dive right into this. Welcome to this explainer, where we're going to objectively deconstruct the exact structural and manufacturing anomalies that led to the tragic collapse of the Titan submersible. Now, we aren't here to speculate today. Instead, we're going to look incredibly closely at the actual material science, leaning on the forensic data provided by the National Transportation Safety Board to understand exactly how and frankly why this vessel's hull failed under the extreme crushing pressures of the deep ocean.
You know, to really grasp what happened here, we have to look at the immediate post-incident assessment from deep-sea expert and filmmaker James Cameron. He absolutely hit the nail on the head, pinpointing our core focus for today, the experimental carbon fiber hull. He pointed out that while the titanium end cap survived totally intact, the composite cylinder was reduced to small pieces. It just highlights the fact that, traditionally, you simply don't use composites for vessels experiencing massive external compression.
So, here is our roadmap for this explainer. We'll start with the experimental hull design, then move to carbon fiber under pressure, look at manufacturing flaws, examine voids in the adhesive, and finally, piece together the fatigue and final collapse.
All right, part 1, the experimental hull design.
Take a look at the physical layout of the submersible here. You can clearly see that central 5-inch thick carbon fiber cylinder bridging the two titanium ends. Now, traditional deep-sea submersibles rely on perfectly spherical metallic hulls. And why is that? Well, a sphere distributes pressure equally all around, avoiding any dangerous stress concentrations. By choosing a cylindrical shape made of carbon fiber, the creators of the Titan were drastically breaking away from literally decades of established deep-sea engineering norms. And honestly, this massive departure from standard practice didn't just fly under the radar. Back in 2018, the Marine Technology Society, which represents the heavy hitters in industry expertise, issued a unanimous, glaring warning. They explicitly stated that dodging third-party validation, like the DMVGL safety standards, and relying on this quote-unquote experimental approach could lead to catastrophic outcomes. The engineering community was deeply concerned about deploying totally unproven materials into such an unforgiving environment without standard certification.
Moving on to Section 2, Carbon Fiber Under Pressure.
So why exactly was this material such a colossal risk? This comparison is absolutely vital for understanding the physics at play. Traditional submersibles use ductile metals, like titanium or high-grade steel. Ductile basically means that under extreme stress, the metal will bend or deform elastically before it actually snaps. It gives you a warning, right? Carbon fiber, on the other hand, is a crystalline composite. It's incredibly strong when you pull it, when it's under tension, but it is notoriously brittle and unpredictable under the crushing, cyclic compression of the deep ocean. When carbon fiber fails, there is no bending. It just shatters.
Which brings us to this absolutely crucial engineering concept, anisotropic. Carbon fiber is highly anisotropic. That's a fancy way of saying its strength depends entirely on the fibers being perfectly aligned in the exact direction of the load. Think of it a bit like wood grain. If those fibers are even slightly misaligned or wrinkled, the material loses its ability to better weight efficiently. This makes it exceptionally vulnerable to microscopic manufacturing defects.
To help visualize how this hull was actually built, notice how they wound dry carbon fiber filaments over a mold. They constructed the cylinder by alternating the winding directions to create this intricate helical pattern, layering it up to about 5 inches thick. Sounds sturdy, right? But as we'll see, applying this specific winding method at this massive scale introduced some severe, fatal vulnerabilities.
Which brings us to Part 3, Manufacturing Flaws and Wrinkles. When the National Transportation Safety Board did their forensic analysis on the trimmed ends of the Titan's hull, basically the leftover pieces from fabrication, what they found was just a litany of terrifying anomalies. We're talking waviness in the fiber orientation, deep wrinkles in the carbon layers, areas where fibers had been aggressively ground down, and extensive porosity, meaning tiny hidden holes or voids. I really want to stress this point. When you are operating in a high-pressure environment, these are not just cosmetic flaws or scratches. They are massive structural weak points. And this visual brilliantly illustrates exactly what those flaws look like in reality. If you look closely at the surface of the carbon fiber under this oblique lighting, you can literally see the waviness and the heavy wrinkles in the orientation of the fibers. Get this. During manufacturing, OceanGate actually had to grind down up to 12 layers of these wrinkled carbon fibers just to keep the hull's shape flush enough to apply the very next layer. Every single time they ground down a wrinkle, they were permanently snapping continuous carbon fibers, instantly degrading the hull's structural strength.
Now check out this specific NTSB data table. It maps out these defects layer by layer, starting from the inner layer, layer 1, and moving outward to layer 4. It's literally a countdown to disaster. Notice how the ground wrinkles jump from just 1 on the first layer up to 8, then 14, all the way up to 24 ground wrinkles on layer 4. These manufacturing anomalies aggressively multiplied as they built the hull outwards. The geometry of the entire structure was inherently destabilizing itself during the fabrication process.
All right, let's look at Section 4, voids in the adhesive.
This side-by-side comparison is easily one of the most critical pieces of forensic evidence we have. The hull was built in 5 distinct 1-inch layers. These layers were co-cured and bonded together with adhesive. Now, on one side, you can see the expected cross-section of the 5 layers. But on the other, when the NTSB actually separated these layers, they exposed these massive, terrifying gaps. See those dark, jagged patches? Those are entire areas where the glue completely failed to bond the carbon fiber together.
To put it as plainly as possible, these elongated voids created discrete, completely hidden zones inside the hull where the heavy, 1-inch thick layers of carbon fiber were effectively unattached to each other. Under normal circumstances, that adhesive is supposed to seamlessly transfer the massive compressive loads right through the 5-inch wall. But with these huge voids present, the layers were essentially acting independently, which vastly reduced the hull's overall structural integrity.
Finally, Section 5, fatigue and final collapse.
We absolutely must understand the concept of delamination here. Because wrinkles in carbon fiber form these soft, resin-rich pockets, they compress way more easily than the stiff carbon fibers around them. When the hull dives and is subjected to that immense external ocean pressure, these soft spots squish down. That causes the surrounding rigidly glued layers to literally pry themselves apart. This peeling apart of the composite layers, kind of like an onion peeling from the inside, is called delamination, and it absolutely kills a structure's ability to carry a heavy load.
Look at this. This is actually a cross-section from an earlier version of the Titan hull, version 1, and it shows severe mid-thickness delamination. Do you see those horizontal cracks just tearing right through the center? This is your visual proof of what delamination actually looks like inside a solid carbon fiber block. It proves how the material, when it's subjected to cyclic pressure over time, fundamentally breaks down from the inside out. It hides the fatal damage deep within the hull wall where no one can even see it.
So when we put all of this forensic evidence together, here's the 4-step mechanism of failure. Step 1, cyclic compression. Every previous dive subjected that hull to crushing pressure and then released it. Step 2, this cycle caused those microscopic wrinkles and massive adhesive voids to delaminate. Step 3, as the damaged areas became soft and peeled apart, the crushing load of the entire ocean was aggressively shifted onto the remaining intact, stiffer sections of the hull. And finally, Step 4, those remaining sections simply couldn't bear the millions of pounds of force all on their own. The result was instant, complete structural buckling and a catastrophic implosion.
Which leaves us with this incredibly powerful summary statement from the forensic analysis. They noted, like a lock designed with a hidden defect, the hull's failure was an algorithmic certainty. It really gives you chills, doesn't it? The Titan's implosion wasn't some random accident or an unpredictable act of nature. It was the mathematically inevitable result of deploying highly defective, unproven composite materials into one of the most extreme environments on our planet.
I want to leave you with this final thought to chew on. If engineering history continually shows us that ignoring established material science protocols and manufacturing standards yields catastrophic results, how do we properly balance the human drive for deep-sea innovation with the completely uncompromising laws of physics? Understanding the hard data we went through today is the first step in making sure we don't repeat the same fatal mistakes. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll see you next time.